and particularly thanks our speaker, Arnaud, who is actually delivering this talk at 10 p.m. his local time from Switzerland. So Dr. Arnaud de la Fortelle is co-founder and CTO of Higgs Technologies. He has designed the vision and technology behind the smart data management, a very powerful way to address the current and future big data limitations. Especially, this is very useful for autonomous systems like autonomous driving, ADAS Industry 4.0, and smart cities. Arnaud has been a professor and director for 13 years at the Center of Robotics of Mainz in Paris, and he has also been a visiting professor at UC Berkeley about 10 years ago. He is an elected member of the Board of Governors for IEEE Intelligent Transportation System Society, and also a member of several program committees and conferences, and was general chair of the IEEE Intelligent Vehicle Symposium 2019 in Paris. He was a member and then the president of French ANR Scientific Evaluation Committee for Sustainable Mobility and Cities, and he serves regularly as an expert on European research programs. Today, Arnold is going to deliver a talk about his company Higgs on the topic of smart data engineering, the future of AI-driven autonomous systems. Arnold, thanks for being the speaker today, and the floor is yours.
Yes, thank you very much for your kind words, Manxi. So it's a pleasure to see some faces. Scott, you were not in Switzerland because we organized a summer school. That was your question. The Cooperative Interactive Vehicle Summer School, the 5th edition was in Switzerland after California. So it went very well. You probably saw the pictures. You missed us. I hope next time you can come to the next CIV edition with some students. So this is a summer school we organized with KIT in Germany and Berkeley for the first edition. So now we have also Tokyo University and the German University of Cairo who co-organized this summer school. But it was very nice. We had also a data hackathon using smart data. But today, what I would like to deliver as a speech is how we can envision the future of AI-driven autonomous system using different ways of dealing with the data. And so, okay. So, what's AI for autonomous systems? So you all know certainly that AI is transforming robotics. So on robotics mean a lot of different types of autonomous systems like industrial systems, logistics, autonomous driving. So I've been in autonomous driving for 2 decades. So this is the one I really know well. And the big problem with AI for that is that you can vibe code a lot of things. It's very useful, but you really can't vibe code your way through autonomous systems because there are many, many more things that you have to do before delivering very smart robotic systems. Typically, I will take the example of autonomous driving throughout my presentation. And again, I don't want to have a talk about mobility problems or the AI part of it, but really about data that we need to deliver the premise of these autonomous systems. And so let's get autonomous driving. You probably all know very well what the problem. Human beings learn to drive in 20 hours, maybe less. And usually people have a very simple representation of driving. That's beautiful drive. But in fact, it's very difficult to automate. I mean, Google stated that they will deliver autonomous driving whatever it takes. When you Google, whatever it takes means tons of billions of dollars. And they have still not delivered 10 years later commercial services. So it's really difficult. I mean, you cannot just power tech, billions of dollars and so on and automate it. And so my question is, because we're about data, Is it because you don't have enough data, or maybe also because you don't have accurate enough data? You have plenty of sensors, actuators, and so on. So maybe with better data, it will be better. That's a real question mark. Because if you take data from real world, again, that's something probably a computation you have made. Typically, because of cameras, you get 5 terabytes per hour and per vehicle. In between, depending on compression, in between 1 on 8 terabytes per hour and per vehicle. So if you do the math, that's not very difficult. You get a petabyte per day for a small fleet. When I say a small fleet, it's dozens of cars. And then you do the math, it means an exabyte of data per year for a testing fleet. Typical testing fleet are in the thousand. And 1 exabyte, if you take 10 terabytes hard drives, it makes 7 Eiffel Towers. So I'm from Paris, so I count the data in Eiffel Towers. That's normal. So meaning that if you continue the math and you get all existing vehicles, meaning more than 1 billion today in the world, it means that you would have more than zettabytes of data. In fact, within 1 year, you would get more data than you have storage in all data centers around the world. So it means that's a really heavy data, so that's big data, and very clearly you cannot do that. It's impossible. Meaning, petabyte per day, and that's what serious companies do. I mean, Google, Cruise, NVIDIA, Mercedes, they all gather about a petabyte per day of data. But then they have to curate this data and reject some data. So they cannot afford to keep all the data all the time. So the point is, it's not sustainable, clearly. It's not either useful, because if it takes 1,000 computers, meaning vehicles, to gather all the data during 1 year, if you just want to replay the data, it will be about 1 year for 1,000 computers. So it would be a very long time just to read the data. So the question is, what's next? And if you look at AI, I will go back in time for people who are too young to remember the very first steps of deep learning on AI. So deep learning, Yann Lequin, typically, it was a NIST data set that was it was 7 layers of convolutional neural networks in the 90s, and it was 60,000 grayscale images, 32 by 32. So it was really peanuts in terms of size of the data set. Okay, I will go fast forward. You have ImageNet and you have the GAN. On there, it starts to be a little bit more serious. 15 million images, but it's very, very simple images again. 300 by 300. Nobody would like to look at any of these images today. And so now you go to large language models on the first version of ChatGPT. So about 30 years, just realize that it was 30 years after the NIST data set on the first attempt to have deep learning. We have that, and it's not a lot. In fact, the first training of ChatGPT was made with about 300 billion words. So 300 billion words, it's half a terabyte. Nothing, you can have it on your laptop. And so that's very powerful. That's a probability theory bias. Would be very happy to know that using billions of conditional probabilities, you can get very smart answers. It represents 3 million books, so it's a lot of knowledge. Who has read 3 million books? Nobody can, in fact. But the question is, what next? So if you go for autonomous driving, you need images, you need videos, you need sound, probably. So you need much more than mere words. So what would be the size of training AIs that really need to have knowledge of vision. That's a difficult question because if you want to learn by seeing everything, it doesn't take 20 hours. In fact, you learn to drive within 20 hours because you don't have two wild countries. But you have to match driving in such an environment, very European, such an environment. Unfortunately, I live in Switzerland. I've never seen that, but it should look like that. But it can be a little bit wilder, this one, or even worse, like this one. Never drove in such a situation, but I mean, people encountering that would probably stop, U-turn on getaway. But would you be sure that an autonomous car or any AI trained with such scenes would take the right decision? I'm not completely sure. So that's what is called, in fact, a plateau problem, meaning that when you train, you train, you train. In fact, at the end, you cannot really learn a lot more. And so the problem is not that big data is not successful, because when you train with terabyte, petabytes, exabyte of data, you better and better, you learn. And typically, driving 101 daytime, summertime is absolutely not a problem for any autonomous driving company today. So there are many things that they can do. Although we still know also that there are plenty of problems. For example, in San Francisco, I will not discuss the cruise problem, but they had a difficult accident and they shut down operations. So GM made a 15 billion write-off because they had an accident. So the edge cases are edge cases, very rare, but they can have a big impact on companies. So it's very important to target a little bit better the data. That's the point. And to finish with that's technical aspect of it. But the economic reality is also that I've talked about data storage, but it's 15% of the cost of the data because you have many, many other things. So if you want to get the value of the data, you require a lot more. For example, you need the security of your data, compliance, governance, labor. You have to pay people, data scientists, excuse me. And so I had an illustration there. So you see that storage is only 15%. So the truth is, if you want to get the value of the data, you have to think of data as really flowing through many steps: curation, processing, and so on, training, testing, and so on. And all this requires specific requirements on the data. That's the first point. So the point is, data is something probably a little bit more difficult than just getting the data, storing the data. You need to do a little bit more on that. And moreover, data is available through, there is a lot of data, like by cars, through the Internet of Things. But when you do to all the processes, in fact, you have the edge, you have the cloud. And in fact, there is a continuum between cloud processing, edge processing, processing within the Internet of Things. And it's something that is called, especially in Europe, that's called the cloud edge on IoT continuum, meaning data is produced by devices, IoT devices, and it can be processed or not, or stored at the edge, and it can be processed or stored or transmitted to the cloud. And in fact, you have many, many nodes so it's kind of distributed computing, but with an heterogeneous storage and computing capacity, because in the cloud, you have a lot of it. And so it's much more than just distributing things. It's a full ecosystem. Again, I'm talking from a startup company, and so we are part of this ecosystem, and we try to find the right place and to win in this ecosystem. So you have today, within this continuum, a unified and distributed infrastructure for computing for all the data processing and also for AI, for training, for testing, for updating, and so on. And you have many kind of nodes from I don't know, very simple devices, for example, wearable devices, to more powerful devices, like a car is much more powerful. Then you have edge processing, all the small boxes that you have on the roadside units, or even some processing, local processing. And you have very powerful cloud data center, AWS, GCP, and so on. Everybody knows that. And now what you want to do there is really to have context-aware computation. Because if you think again of a concrete example, autonomous car, you may have latency, so you cannot drive the car and do all the computation in the cloud. It's impossible. You have also data sensitivity, especially in Europe, but not only. You don't want all your data to go anywhere. Network conditions, if you drive in the mountains, so I live in Switzerland, so sometimes you have almost no coverage, but you still have to drive. Energy constraints, you cannot consume megawatts in a car. And even more important for people like Path, you really need efficient real-time decision making close to the data source, meaning the driving decision should always be within the car, so that you don't depend on communication or external data sources. So it's very important for security. So understanding this is really foundational for the next-gen applications, because you cannot see the next-gen AI by just querying big systems like ChatGPT or Claude or whatever, Gemini. So you will need probably very powerful AI in the cloud, and also less powerful but more specific AI in all the systems, in the edge, in the IoT, and so on. And that's a real enabler, because nobody can envision any autonomous system without AI. It's absolutely impossible to go back. So just a pointer for the European site for that. So now the problem is big data and AI problem stem from in fact, the cloud capacities. When all the cloud performance were built from the first AWS servers that were just about data storage to much more complex processing apps and so on. Now in AWS, you have many things that you can do. Meaning you wanted to solve all your problems by sending all your data, training your AI, processing your data in the cloud. That was the best way. That was the big data approach. It worked, and it works still. But now, as for autonomous driving, you cannot drive a car with only this cloud infrastructure. So that's a problem. Edge computing also is, so it's no longer optional, but even if you can have real-time AI inferences at edge, there are some inferences that probably some supports that you will need from higher level AI systems that can support autonomous driving. Infrastructure is important, not only the physical infrastructure, but also some digital infrastructure. And so edge computing is important, but the continuum is not to make a trade-off. It's really to use both the edge and the cloud, because you cannot, as for autonomous driving, you cannot decide to do everything in the edge or everything in the cloud. So you really need to distribute things on a very smart way of doing that in between the edge. So it's not only an hybrid approach, but it's also a dynamic approach, because some processes will be run on the edge, and then you need maybe sometimes more power. So you will go to the cloud, and they have to communicate. This is true for processing. This is also true for data management. And so you have to find a way to distribute the data in a smart way in between the edge and the cloud. And that's the challenges that exist today. We don't have all the solutions for these challenges, and these are new challenges. So the first one is the architecture. How do you design an architecture between, for example, IoT, far edge, regional cloud, global cloud? So you know that everybody wants to have its regional cloud. You go to Geneva, for example, for mobility, and they want to have the data of Geneva in Geneva because that's Switzerland and Geneva is a state. So they want their own data. And then you have probably a cloud for Switzerland, and then you will have a cloud for Europe, and then you have a global cloud. And so that's difficult to think of that. How do you balance performance and orchestrate all the processes, all the data pipelines between all these nodes? Of course, many other factors to consider. And this requires really rethinking, especially for data, the data pipelines. I hope you have seen cruise vehicles before the shutdown, but when I visited a cruise facility in San Francisco, they were just getting the data by removing the hard drives and then putting an empty hard drives in the trunk. And they did that with a trolley. I mean, that's really a data management from the Middle Age. So you need better data pipelines. And again, Cruise did very well with the data pipelines. They had a fantastic processing, even though they made a big mistake. But in terms of technology, they were really good. And it's the same, by the way, for almost everybody. They take the hard drive and then take it. So processing, model placement is very difficult. The design of the infrastructure itself, because of course, big players like Waymo, they don't care. They want to rely on the cloud because that's where they make money. It would be the same for AWS or for Microsoft. So we really need for next-gen AI, context-aware deployment. On that, again, when you want to federate everything, you want to federate learning, you want to federate processing, meaning to distribute, and you want to also to distribute data, but meaning when I say to distribute the data, to distribute the data processing. So to have really adaptive systems that can deploy and redeploy depending on where you drive. Because typically, if you drive downtown San Francisco all the time, and then you drive to the Sierra Nevada, you probably need a slightly different driving mode. So maybe you will upload new capacities to drive, especially in wintertime. You need very different abilities. And so there will be context-driven intelligence and at scale, and that makes the challenge pretty difficult to predict how this will be really done and supported by all the AI we know and that will be developed in the close future. And so smart data is just about this paradigm shift. And to define something is smart data is synthesized pertinent data, meaning pertinent, it has a purpose. You don't gather the data because you want to have all the data. You gather the data because you know you want and you need this data. Big data is just you get it all. I mean, big data is you want to have a needle, so you get a haystack because there is a needle somewhere in there. Smart data would be, okay, let's get needles instead of hay. But I mean, again, big data works a lot. So how biggest problem we have, even as a company, is what is the relevant data? And some of our customers, one of the first question is, okay, tell us because you're the expert. But I say, okay, no, we're experts in data management, but not in the management of your data. You're the expert. So you need to define what's relevant. So there is still some work, even if you have tools to do that. And the question is, what do you need? What do you want to learn typically? Because you have to concentrate on something, because learning everything is not a good idea. It's not feasible. And also, big data strategy is broken. As I said, you cannot have zettabytes of data on learning from that. It's impossible. So you have to be a little bit more focused. And so the other is really small data. And so when I try to define, I wanted to do it a little bit more technically. So relevant means also interoperable, because you will have many processes. Typically, you may want to transform your data from big data sets into tensors for training. But also it has to be light so that you can exchange data. Typically, Tesla gets data from all Tesla cars, but you never see Tesla drivers getting a hard drive and putting the hard drive on internet so that Tesla can download data. So it has to be light, easy to process, and probably also collaborative so that people can exchange data. So if, in other words, I say exactly the same, but with technical words, it's an event-driven, agile data pipeline based on the continuum, meaning that can really flow. That's what we try to build at X Technology, and to provide to our customers a data pipeline that they can customize to their needs and that they can use not only for research, but in the future also for deployment, large-scale deployments. And so we also have that's a technical vision. We also have a social vision on that's very easy, because I explained to Maxime, maybe everybody was not there to explain the hex sign, but Higgs was chosen because Higgs in French is the same as X, so it's the same pronunciation. The letter is called X. And it was to cross technology development with also sustainability, so not to produce more impact on our planet by developing technology than we solve as a problem. And so the problem, of course, we want to solve this Eiffel Towers of hard drives problem. So we are committed to decrease the impact. That's something we want to do. And it's not so difficult theoretically, because there is a statistics with the data that if you have not read data within 3 days, 72 hours of its generation, it will never be read in 95% of the case. So after 72 hours, 95% of your data will never be accessed. That's bad statistics, I would say. And so what we can do is remove unnecessary data, and we believe we can remove 99% of data, because when you drive straight, you don't have to learn. You have to learn when there is a problem. You can also say, okay, I've extracted the data, I have processed the data within my pipeline, and now this data is still there, but it has been used once. So I will keep it in case, but I can put it in cold storage. Today, when you use AWS servers, all your data is on hot storage. And that could, in fact, make quite a lot of impact, because we have estimated that if we could do that for autonomous driving companies, it would be more than 1 million tons of CO2 per year. So that's an impact we would like to have, not yet. And so our solution within one drawing is, you have on the left the data generation on-premise, in simulation, at the edge, or whatever. We put in these devices, smart devices, agents. So one agent per device. So if we have 1 million cars, we have 1 million agents. And then all these agents, they discuss through APIs, of course, to storage, of course, and also some other processes, so that we can ingest directly the data to the pipeline of the customers. And okay, that's how it works. So if you have question, you can ask. I have a little bit more details. So you can see that usage of the data can be for MLOps, for diagnostics, for analytics, and so on. Analytics, okay. So how the agent work to produce events, that's very simple. You have on the left the cloud or the edge. So imagine a vehicle. The vehicle produces a lot of data flows, of signals. I will tell you, you probably cannot imagine how many signals are in a real car. And then we have our components. We have a monitor that catches the signals, make it available to our smart data engine. And whenever a combination of signals satisfies a trigger rule, then we record the data, all the data or some part of the data. So very simple, just signal, monitoring, recording, and whenever there is an event, you produce a smart data, meaning the data itself, typically pictures, videos, sound, lidars, whatever you want, and you send it to the cloud together with metadata. And the metadata part allows to have a very fine-grained processing later of the data. You can add tag whatever you want. So now the question was, I don't know if people are able to answer, but we work with car manufacturers, and we had access to testing car using ROS, so very practical because we can subscribe and list all the topics. Do you know how many signals were available in a ROS bag that we got? Someone? No? Too difficult when I'm remote? Okay, so I will answer. More than 100,000. More than 100,000 signals. So meaning the combinatorics of all the triggers that you can build is huge. There are so many signals that even the engineers of the OEMs, they don't know about them. When you have 100,000 signals, you cannot even use AI to make a request because you're out of token before charging, in fact, the definition of all the signals. So it's a real problem. In fact, when you start working with real systems, on why you have 100,000, because a single smart camera produces more than 1,000 signals for one camera. So that's a lot of signals. So that's a problem. And so we made, I wanted to show you some concrete examples. So we made a small implementation with Scala. Okay, so you know Scala, I don't explain. And now, okay, again, if it's not interactive, I can ask you, but there was a trigger. It was an intern driving the Scala simulator, and he wanted to trigger the condition. So the condition was a Z acceleration because it was bumping on the side of the road. So that's why he drives so crazily. When you have such events, so you can record 5 seconds before, 5 seconds later to understand why there was an incident. So for example, a vertical acceleration in that case. And you get the videos of what happened, but also a lot of contextual data because we use a ROS bag most of the time when it's available. That's typical smart data strategy. So practically, if you want to engineer the things for customers or for yourself tomorrow, what you do, you plan your data collection. So what is relevant is a trigger, it's a condition. Where to get the information that the systems, so your car, your simulator, or even a replay, you can have ROS bag that you replay. We made ROS bags available with Tokyo University for people to be able to play with that. Then you implement and deploy the agents in systems. The good news is when I say implement, if you use ROS2, there is no implementation because everything is already provided. The agent is natively able to read and to record ROS2 topics. Then you run your system, so you drive your car, you drive your simulator, and you gather your smart data. And you can have typically a few dozens of triggers for special events. You will get, in that case, a few dozens of data sets. And if you run your system for a month, you will get thousands, millions of events. And then you get statistically significant data sets, one per trigger. If you're a commercial company like Tesla, you have something like in between 500 and 1,000 triggers. So you have very specific data to train or to make analytics with that. You analyze your data, and in fact, you can refine. Imagine you want to have pedestrian because you're not fluent in pedestrian detection. you put a pedestrian trigger. After a while, you probably have so many pedestrians that you decide that having pedestrian daytime in front of you when it's a traffic light, you don't care. So you remove all those pedestrians by refining your trigger. You say, I want to have pedestrian, but only during nighttime, foggy time, the rainy day, or whatever. And that makes a loop. So why we need a data pipeline, because when you have used your data, for example, for the pedestrian are okay. What you need is edge cases for pedestrian. So you have to reprogram, in fact, your triggers, build a new data set that's much more focused, and iterate this approach. And it works pretty well. And that's what we do with our customers. And so smart data in the continuum is about having our agents are completely deterministic. Triggers are completely deterministic, but our agents are deterministic, but AI ready, because what you can do is deploy edge AI to detect anomalies. On the anomaly signal, you can catch the anomaly signal and raise an event in that case. So it's very easy, in fact, to have a non-deterministic usage of our system if you plug an AI on previous signals this way. What you can do also, you can pilot the agent through AI, because all the conditions that you put that you want to change, you can change very quickly. In fact, all your conditions, you can reprogram your agent. You can pilot that with an AI, saying, okay, I don't want this data anymore, but I want to activate this trigger. Typically, you want pedestrian. When you drive on a highway, you don't need to have the pedestrian trigger active. Typically, you want to have people in snow. I believe in Tucson or Phoenix, you can deactivate that trigger, probably very seldom. And then we have this flow of data that goes from your system to our cloud, and then to the system of the customers. So we don't keep the data. And you can exploit that with various processes. So that really enables versatile data pipelines on one of our customers. It's a public customer, so it's RTP, so it's a mobility operators in Paris. They use our solution, and they said the big change is they had event detection, of course, already implemented, but it took them like 3 months to change the conditions. And with our system, within minutes, they can change the conditions, so it's much more efficient. So to get to the end of my presentation, because I believe it's time, if I want to have some questions. Data is not about training, using. It's really also about sharing, trust, and cooperation. Why? Because data sets, you can build hundreds of data sets, and some can be shared, some will not be shared. Typically, we had a discussion with San Francisco Transportation Authority, and they have plenty of autonomous cars driving in San Francisco. They have absolutely no data, because people say it's commercial secret. It's our operation. We cannot provide you the data. But imagine that they have 1,000 data sets. Maybe one data set could be shared with the public. They can curate the data set before providing to the public. Maybe some events will be curated, but they could provide this way. And they could provide also with providers. When you're a car manufacturer and you work with tier one, the tier one, they also need the data to improve their devices. So the question is, what kind of data can you share with them? Currently, they don't share a lot of data. It's a problem, because you lose competitivity if you don't share the data. And very important, data is key to evaluation. If you share the data, if people are confident, if you're not self-evaluating yourself, because evaluation can be negative. Everybody think of data like an exam. Nobody likes exams, but you know what? If you don't pass exams, you never get diplomas. So at some point in time, you need this evaluation. For the driving license, same. So this is key, but also it's key to build trust, I say, and transparency is key. And so we work with transportation authorities, for example, with the ADS project with Berkeley, Contra Costa Transportation Authority. We work, or RTP, but that's more French. Industrial robotics, we work with robotics companies, but also with manufacturing companies um, or that. And the good news is you can use the tool. So just one word of advertisement, just go on x.io, you will have the slides you can check. And in conclusion, last slide. So if you really want to think of the data in the continuum area, you have to stop thinking of the data as something that you have to catch and then to process. Data it's flowing all the time. It's already there. And I mean, a very good example is Tesla. They're really great at processing the data. But with AI progressing on the appetite of data for next generation AI, we will have more and more problems with the data. And so we have to find new ideas. And so a transition is necessary. I don't know exactly how it will happen. I'm trying to guess. It's very important for X. But at least we have a continuum ready data solution at Higgs. So that's very important. But it has to be combined with many other technologies. So that's why we have partnerships. That's why we want to have exchanges with academia. And that's why also I'm here tonight today for you, because I want to have these exchanges. In fact, I have these exchanges because we work with Peggy, we work with Scott to have the summer school. I had Alex Bayan at home this summer. He spent a few days with our family. So we discuss all that, and we really need to build this ecosystem. It will not be made by some companies, even very powerful in the US or in China. We need many, many companies. And I end with some French words. L'avenir n'est pas ce qui va arriver, mais ce que nous allons faire. So for those who don't understand French, it's the future is not what will happen, but what you will make of it. So I hope we will make the future with Higgs, with Berkeley, and hopefully together. Thank you for your attention.
Thank you very much. So let's open for questions, and for people who are in the seminar room, you can just directly talk. Are there questions from the audience in the seminar room?
I have a question that may be a little bit of a summary of kind of the overall data strategy. So there's some amount of smart data that needs to go back to the companies that can use it for development of new products. The other data, is that deleted? Do you envision that being all stored on the machine and then at some point put into cold storage? What's your impression, and what do you think kind of the folks you talk to in industry might think?
So our usual talk is to tell people you can keep all the data, because some people are very, very they don't want to lose data that could have value, but it's just fear. I mean, statistics show it's completely useless. So if you really want to, I mean, if you have KPIs, if you would have more KPIs for your data, you would never do that this way, because you waste, in fact, storage and so on. But the storage is very cheap, so it's not a big deal. So what we say is you can keep your pipeline where you store all the data for a while at least, but you can put our solution on top of it. So, okay, it means we duplicate the data. So for impact, it's very bad, but we duplicate probably. There is the 100% that they keep, and then there is a 1% smart data that will be much more agile and that they can use. As soon as you're comfortable with the new process, you can switch to an all smart data approach if it works well. I mean, probably you will lose a few events of interest. You will lose if you delay the data. But you know what? When it takes you days to get the data in storage. I have tons of stories that I can tell you all of them, but some companies were testing, until they extract the hard drives, they send it by plane to data centers in the US, and then they analyze the data. Sometimes they have incidents that they discover only 3 days later. One public incident that was known is there was no crash, but a car drove on the sidewalk for 15 meters one day. And they discovered that 3 days later. Now, that's insane. You cannot have such a kind of event management. And so that's where you see fearing to lose the data is to be weighted with having access to the right data at the right moment. Defining, so stating that you need to give the right data to the right person at the right time, that's already an agile pipeline, data pipeline. So you will need something like our solution. Maybe other solutions, there are. We have competitors, but you need something much more agile than just a big data approach.
Yeah.
All our customers, they ask that at first. So usually we deploy our solution in parallel with their legacy data pipeline, and then they migrate when they're comfortable.
Okay. Yeah. I have a question. So the event, the trigger-based data filtering, I think there is an implicit assumption is that when you give the context to the algorithm or the agent can understand it and filter the video data. So in some cases, this means that the data set that you have is very easy to label. But in some other settings, for example, if you describe a complex event or environment to the agent about a particular traffic condition in the data set, it may not be so easy to label whether this video is yes or no for the context that you describe. Have you encountered that
Yeah,
situation?
completely true. So again, our solution is deterministic. So if you have a signal, you have to use a signal to raise a trigger. Typically, if you define a hard brake, then you will get the acceleration. And sometimes you have several acceleration in a single car. So you will get the acceleration and say, okay, if it's above the threshold, I don't know, for example, 4 meters per square second, that's a harsh acceleration, then I will trigger the event. But very precisely, the real difficulty is not to define the trigger, because you can define many triggers. The difficulty is to set the right thresholds. Because if you say, okay, I will set the threshold at 4 meters per square second, and you say, oh, I lose too many events, so I have to decrease the threshold to 3.5 or 3, whatever. It means you have to reprogram all your systems. And again, maybe you have not a single car, but 1,000 cars. So it's very important to have a system where when you change the threshold, you can very quickly redeploy the configuration to all cars and get the new events. And so that's what we managed to do, to reconfigure very quickly, in a matter of minutes, in fact, of seconds, if you want, and iterate quickly, because, as you say, you want something, and it's extremely difficult to express technically what you would like to have, because once it's written technically, you get what you have written, not what you want.
I see. So have you encountered the situation that you need a human to label the data in order for you to process?
No, in fact, no, because we don't trigger events through labels.
Okay.
We trigger events through signals. Now, it's about the same, because when you have a label, if you want to have real-time labeling, it's kind of edge AI agent. So in fact, we have developed a solution where we have the edge AI agent to trigger I would say events using an AI or not using deterministic signals. But it's very experimental, because when you do anomaly detection, the very definition of an anomaly is
Mhm.
ill-defined. You
Mm,
don't know what is anomalous. It's
sure.
impossible to have a technical, precise definition of that.
Mhm.
So we do our best. We say, okay, maybe try it on if it's good enough, go with it. But we don't want to sell it as the perfect solution because it's impossible.
Okay. Scott.
Yeah, first, Arnaud, thank you for this excellent talk. And thank you for your leadership too in the community, including this summer school. Really appreciate it. This talk was super interesting. And first a comment and then a question. The comment is, I love this problem that you've identified of big data, smart data, the utility of triggers. And the comment is I've experienced this as a customer. You mentioned Tesla a couple times, so not anymore, but I had the FSD supervised, and I notice when you disengage it, it's a trigger, and it seems to take the last whatever 20 seconds of data. And since Massi and you were just talking about human annotation, the other interesting thing they added is that you can do a voice recording. It encourages you to do a voice recording of what you observed in the moment of the disengagement, which is kind of interesting. So, that got me thinking about the utility of these triggers and how that's done. So I think it's really cool and it seems very useful. My question is, it seems the trick is how you design the trigger. And there's always a trade-off between how much data that you send up to the cloud or you process, versus how much information is useful. So I'm wondering in your company or in, maybe in the academic literature, what is a good way to think about trigger design? Because it seems like that's ultimately the key for any user here.
So my conceptual, thank you very much for your kind word. It's a pleasure to be in this community. In fact, I'm very engaged with the ITS community. Trigger design is, I believe there is no final answer to that. Usually we start with disengagement. That's the simplest, so you're completely right. That's the simplest trigger that you can have because it's always interesting. So you have to start with that. But then what you would do is to analyze the root cause of the disengagement. And when you get the root cause, for example, you say visibility was very poor. You can have signal for visibility. There are some measurements of visibility, distance of visibility. So you say, okay, now I want to record all events when my visibility is below, I don't know, 100 meters. It's very foggy or it's very rainy. And I drive in a sloppy or curvy drive, not highway. And in that case, it's two signals that you can measure probably, one with a map, the other one with the sensor. And then instead of recording only the disengagement, we will try to record the root cause. And when you do that, a lot of time, what you build is simply a failure tree. So my vision is you build a failure tree. On the failure is disengagement, so impossibility to drive. That's very bad. So meaning you have to stop or to find a safe position. And your failure tree will be absolutely gigantic at the end of the day. So some events, so meaning you will have probably thousands of leaves if you do it seriously. So my vision is in the future, by constantly learning the failure tree, you will develop more and more triggers that will give you insight of what may cause future incidents. Because if you can catch situation where your driving ability are below the current state of your driving, then it means you should decrease your speed or you should stop before there is any incident. And this failure tree, of course, you can do it manually at the beginning, at the very beginning, but I'm absolutely sure that more and more people will use AI to build this failure tree and to maintain it. Do I have enough data to be sure that this is the root cause or it's not the root cause? So it will be a very dynamic and probably a topic, how to, as you say, how to choose the trigger.
Interesting, thanks. So in the room here, at least, I think we have to switch over to our next activity in the room. So we might have to sign off here unless there's any other quick questions in the room. Okay, as our host, Muncie, I'll
Okay.
turn.
Okay. Let's thank our speaker again, Arnaud. This is a wonderful talk, and thanks for the very interesting conversation as well.
Thank you very much for the invitation, and it was great to be back at Berkeley, even virtually.
Yeah. Okay. Great.
Thank you. Have a good day.
See you.
Thank you.
Thank
Good
you.
night.